In the last lecture, we had started talking about one of the most important properties of transforms, which is that of compressibility or energy compaction. And I had motivated it to some level. Let's now formally define the notion of compressibility or energy compaction. So just to remind you, we are talking about n-dimensional signals. So we are in Rn, x belongs to Rn. Our transform is given by U, which is an n by n matrix. And we have the usual properties that U Hermitian U equals alpha, U Hermitian equals alpha identity. So it's an orthogonal transform with this special structure. And if alpha equals to 1, then it's an orthonormal transform. And my transform is given by x hat equal to U times x, which is also n-dimensional. So to talk about energy compaction, we first say that we are given x hat k, where k equal to 0, 1, up to n minus 1. And we sort these coefficients by their magnitude. So we put the one which has the most energy first, then the next one, and then the next one, and so forth. So an example will be if you have, for example, at 0, 1, 2, 3, then 0, 0, 0, 0, 8, and then 9. So if these are your indices of your coefficients 4, 5, 6, 7, 8, 9, 10, then the largest coefficient is x hat 3. So x hat 3 absolute value. We are always interested in absolute value. So these could have negative values, but because of just convenience, I only plotted positive values. So x hat 3 is greater than or equal to x hat 1, which is greater than or equal to x hat of 10, greater than or equal to x hat of 0, and all of them are then greater than or equal to the rest, which are greater than or equal to 0. So the idea of energy compaction is that you sort your coefficients in the descending order by their magnitude. So the largest coefficients go first, and of course you have n of them. And if we throw away all the coefficients, or effectively set all my coefficients equal to 0 except the largest k ones. So if we keep only k largest coefficients and set the rest to 0, then most of the energy in the coefficients is still contained in those For example, the total energy of your transform, right, it's given by k equal to 0 to n minus 1. x hat of k square. Okay, that's the total energy in your transform, and by Parseval's relationship, that is directly proportional to the total energy in your signal. Now, a transform has the energy compaction property, or it does this compressibility of your image if you can keep only k of your coefficients and set all of the rest to 0. In our case, most of the other ones were already 0, but even if they were not 0, they may be very small. So if you set all of them to 0 except the k largest, then the energy in those k coefficients is enough to capture most of the information in your signal. Now, information in our signal, we try to think of it in terms of energy. So the idea is that this energy in all the coefficients is roughly equal to if I just kept the k largest, so x hat k square, such that this k corresponds to k largest coefficients. Okay. So in this case, for example, if my k was 3, okay, then which coefficients we will keep? We'll keep x3, x1, and perhaps x10, and we'll set all the other 8 coefficients equal to 0. So these ones were already 0, 4, 5, up to 9, but we'll set also 2 and 0 equal to 0. Okay, and because of the fact that we threw away some coefficients, we'll lose some information. Now, if I make k equal to 4, then I'll keep this 1, 3, 10, and also 0 coefficient. Still, I'm losing some information, but less than the previous case. And if I keep my k equal to, for example, 5, then these 5 coefficients are enough for me to capture everything. So the energy in my coefficients is exactly equal to the energy in x hat of 3 square plus x hat of 1 square plus x hat of 10 square plus x hat of 2 square plus x hat of 10 plus x hat of 0 square. There was supposed to be x hat of 2 here, which I missed. So that's the idea of energy compaction, that you keep only a few of your coefficients and that's enough for you to reconstruct your original signal. Okay, and transforms which capture most of the information for small values of k are better than transforms which require larger value of k to capture all the information. And the advantages of that are manifold. You can use them for compression, for example. Think of it this way, that in this example, there were 11 coefficients, but you only need to store 5 of them, right, rather than storing 11 of them. And that is enough for you to recover everything. So compression is an immediate area where compressibility or energy compaction comes into play. It also helps us in other areas, but we won't go that much into that direction because that is more in the statistical side of signal processing. Like, especially if you are doing denoising, it again, compaction or compressibility helps you a lot. Okay. So formally we can think of with the energy compaction or compressibility, the term that goes is k-term approximation of a signal. So remember how we use the transform to reconstruct our original signal. We have x, which is given by x0 up to xn minus 1. That is equal to simply u Hermitian x hat. So that's the inverse transform expression divided by alpha, which is the scaling factor. Now, this u Hermitian, this is again an n by n matrix, so I'll just write it in terms of its columns. So it's 1 over alpha times, let's write columns. This u0 is one column, u1 up to un minus 1 times x hat. So you have this as an n by n matrix, and I'm writing this as collection of n columns where each one of these columns is an n by 1 vector. Okay, if I think of it this way and I expand my x hat as x hat 0 up to x hat of n minus 1, and I think of each of these columns as nothing more than just an n-dimensional signal itself. So if you have a matrix multiplied by a vector, that is simply equal to the summation of all the columns which are weighted by the entries in your vector. So I can write this as 1 over alpha summation of k equal to 0 to n minus 1 u0 x hat of k. Okay. So now this x hat of k is a scalar. So what is the interpretation? That my x, my signal, n-dimensional signal, is just a linear combination. So this is just a scaling factor. Okay. Linear combination of n vectors or n signals. So I can think of each of these as an n-dimensional signal. So my x is just a linear combination of n signals. The signals are given by columns of this matrix U Hermitian. And the k-term approximation is defined as the 1, so your x of k, which is the k-term approximation, is one in which we use no more than k UIs to construct my original signal x. Okay. So the idea is that instead of using n of these u's, you just use k of them. And if you just think about it, the natural, if you want to use the best approximation, the idea is you use the u's which correspond to the largest. Sorry, in this expression it should be u of k, not u of 0. So if you want to construct a best k-term approximation, the approximation which is closest to your original x, you should use the u's which correspond to x hat k's which have the largest values. So in the previous example, if you go back, if you were given k equal to 5, you should use the u's which correspond to x hat 0, x hat 2, 1, x hat 2, x hat 3, and x hat 10. Because if you use others, then they are not going to contribute that much to the information. Okay? So the best k-term approximation is formally defined as let's use x star of k. It is defined as 1 over alpha summation of u of k x hat of k, and k belongs to, let's say, some index set I. So you are not going to use all the k's. The index set I is defined to be k such that x hat of k absolute value is greater than or equal to the remaining n minus k coefficients. So you pick the coefficients which are largest in amplitude, and you construct an x star of k which is constructed by using only the UKs that correspond to those. Effectively, you are setting the other coefficients equal to 0. Okay. And then you measure the error in terms of, for example, error between x vector minus x star of k vector. This is a n-dimensional vector. The 2 norm squared, which is simply equal to n equal to 0 to n minus 1, x of n minus x star k of n, absolute value squared. Okay. So if your transform is good, if your u was good, then this error will be really small for reasonable values of k. Or for the same value of k, if you have a transform for which this error is smaller than another transform, then that transform is better than the one which gives you a larger error. Okay. And again, as I said, the purpose is that if you can use only a small number of UKs or alternatively x hat k's, then you only have to store a small amount of information. You don't have to store everything. Okay. That's the obvious reason to use it for compression. And of course, you can use it for other purposes, denoising, classification, or other signal processing applications. So let's take a look at examples from what we already know to give you a better sense. So let's say your capital N equal to 10 and your xn is a constant signal, xn equal to 2 for n equal to 0, 1 up to 9. Okay. Now, okay, so if you look at this signal, it's itself non-zero. It's a constant signal. It remains from 0 up to 9. It takes the value 2. Now, let's assume that U is the discrete Fourier transform. So U corresponds to the DFT matrix. What's the DFT what's the discrete Fourier transform of a constant signal? Which of the coefficients will be non-zero? Only the first one. right? The Fourier transform of a constant signal is just a delta function at k equal to 0. So only your x hat of 0 will be non-zero, and that will be equal to simply n equal to 0 to n minus 1 xn. That will be equal to 2 times n, which is 20. Whereas x hat of k will be equal to 0 for all k equal to 1 up to 9. So is this signal compressible, or does DFT do a good job of compressing this kind of a signal? And the answer is, of course, yes. You only need one coefficient to know everything about the signal. So your x is simply given by u0 times x hat 0 over n. Alpha, in the case of the way we have defined DFT, is n. Right? U0 is the only one that we need, and you get back your x. Okay? So this is k equal to 1 k-term approximation which is not even approximation, it's exact. Right? Similarly, you can take any other signal, let's say xn. So this is the case where it was a constant. Now take an xn which is a complex exponential. So let's say xn equal to 5 e to the j 2 pi by 32n, and take capital N to be equal to 64. Okay. Is this compressible or not? Well, again, if we write it in the right fashion, if we express it as j2 pi, so 32 is, I can write it as 2 by 64, that's 2n. So this is nothing but a complex exponential whose frequency is exactly equal to one of the frequencies that the discrete Fourier transform computes. Right? Discrete Fourier transform frequencies are omega k equal to 2 pi k over n. So this is a complex exponential with frequency omega naught equal to 2 pi by 64 into 2. So it's indeed just one frequency of the discrete Fourier transform. In particular, if you were to compute x hat, you will find out that x hat k equal to 0 for all k equal to 0, 1 up to 63, except x hat k when k equals to what? And k equals to 2. So all of your DFT coefficients for these kinds of signals are going to be 0 except one DFT coefficient. Again, your x can be simply given by that DFT coefficient. So that DFT coefficient will be, if you were to plot the DFT coefficient, it will be 0 at 0, 1 at 0. At 2, it will take its height will be 5 times n. At 3, it will be 0 and so forth up to 63. So x is simply given by x hat of 2 times u of 2, the vector u of 2 times x hat of 2 divided by alpha, which is n. Okay. So again, in this case, your signal is simply very well represented by simply using one column of your transform or one transform coefficient. The terms are interchangeable. I can say you use one column or you use one transform coefficient. Right? So this is again a k equal to one term approximation. In general, the thing is that if you have signals which are pure sinusoids, for example, of pure complex exponentials, DFT does a rather well job of compressing them. Okay. And in general, you can actually go beyond pure sinusoids. You can say signals which are smooth. And smooth I have put in quotes because smooth simply means that they don't vary that fast. They have perhaps some sort of a differentiability condition. They are not going to rapidly spike up or down. As long as you have smooth signals, then they are well approximated by k-term approximations using the DFT. But even within the class of smooth signals, it turns out that you can do better by going beyond DFT and actually talking about another transform, which is the discrete cosine transform. So unlike the discrete Fourier transform, which tries to express your signal as a superposition of these complex exponentials, discrete cosine transform tries to represent your signal as a superposition of cosines. And because of property that we won't go into, discrete cosine transform does a much better job of compressing your signal or of capturing most of the energy in small number of transform coefficients. Okay. So if the same amount of energy DCT, the discrete cosine transform, captures in, let's say, 10 coefficients and DFT captures in 20 coefficients, then of course you can use only 10 coefficients in DCT versus 20 in DFT. You should prefer DCT for a number of tasks as compared to DFT. Okay. So DCT, or the discrete cosine transform, has many definitions. There are variants of discrete cosine transform. What we are going to study here is called the discrete cosine transform 2. You shouldn't confuse that with the two-dimensional discrete cosine transform. They have this factor of 2, of course, but they are two different things. And we won't go into the details. Discrete cosine transform at some level is closely related to the discrete Fourier transform in terms of you can define it just like the way we define discrete Fourier transform by taking a signal and periodically repeating it and relating it to the Fourier series. But we won't go into that. I will just give you the direct definition. Discrete cosine transform, which is again an orthogonal transform. If you are given a sequence xn, it's given by x hat of k equal to 2 summation of n equal to 0 to n minus 1 x of n cosine of pi k 2n plus 1 over capital N, 0 less than or equal to k less than or equal to n minus 1. So instead of projecting your signal onto complex exponentials, discrete cosine transform works by projecting your signal onto these cosines. And if you want to write down the u in this case, that is simply given by, you just look at the entries in here and you construct those rows. So the first row of this will be 2 cosine of pi 0 times 2 times 0 plus 1 over 2 over n, 2 cosine of pi 0 times 2 times 1 plus 1 over n, and so forth. 2 cosine of pi times 0 is 2 times n minus 1 plus 1 over capital N. So this is the first row of your DFT, of your DCT matrix. And similarly, you can construct the other rows. The last row will be 2 cosine of pi times n minus 1 to 0 plus 1 over capital N. And similarly, you can just extend each of the entries. So this will be 2 cosine of pi n minus 1 to 1 plus 1 over n, and 2 cosine of pi n minus 1 times 2 n minus 1 plus 1 over capital N. Okay? So you can write down and you can verify, you can multiply the columns of this matrix and you will find out that they are orthogonal. But this U, orthogonality of this U is not in the form that we had discussed. It's a little subtle. You can't simply write it as U Hermitian U equal to alpha identity. So for the DCT, a better option is to work with the orthonormal transform, which is that, so you can make it unitary by actually dividing each column by its norm. Okay, so making this U orthonormal, which simply means that the energy in each signal is 1 and the inner product of the different columns is equal to 0, unless you are taking the inner product of the column with itself. The unitary version of DCT, which has U Hermitian U equal to U times U Hermitian equal to I identity, and we can take the Hermitian to be equal to transpose because it's a real valued matrix. X hat k in that case can be simply written as square root of 2 over n beta tilde of k summation n equal to 0 to n minus 1 x of n cosine of pi k 2n plus 1 over 2n. Where this thing is actually a function of which row you are dealing with. So this beta tilde k is equal to 1 over square root of 2 for k equal to 0 and 0 otherwise. So if you actually compare it to this earlier formula, this one that we had written earlier, which is not the unitary transform variant, this one compared to this one, the main difference is that this 2 actually becomes 2 over square root of n. Okay, if you want, and the other thing is that there is another scaling factor, beta tilde k, which in the first row makes an appearance but doesn't appear in any place else. Okay, so in the first row that is 1 over square root of 2, and in the other rows it doesn't appear. So this square root of 2 over n, 2 replaces square root of 2 over n in all entries, but there is an additional factor of 1 over square root of 2, which is only in first row. All the other rows don't have that 1 over square root of 2 factor. If you want to generate this unitary matrix in MATLAB, you only have to, the command is dctmtx_n. Okay. So if you give it dctmtx10, it will generate this DCT matrix, the unitary one. And computing the DCT coefficient is as simple as you simply take your signal, multiply it with this matrix, and you have your DCT coefficients. Okay. And the inverse in the case of the unitary variant of the DCT, inverse DCT is given by, so I'm giving the formula here. You can simply use the U transpose expression to actually find out that each entry is simply this vector in a product with your coefficients. Because in the case of the unitary matrix, X is simply equal to U transpose X hat. So we can write that entry-wise 2 xn is equal to square root of 2 over n summation k equal to 0 to n minus 1 beta tilde k x hat of k cosine of pi k 2 times n plus 1 over capital N. Okay. So beta tilde k should be equal to 1 otherwise, yes. Okay. Okay. And this is the inverse DCT expression. Okay, so what we now want to do is an example where we demonstrate that DCT indeed is better than the discrete Fourier transform in terms of compaction. So the example is of this xn, which is 0.9 n cosine of omega naught n for n equal to 0, 1 up to 31, and omega naught is simply 0.1 pi. And what we want to do is simply take the discrete Fourier transform of this signal, take the discrete cosine transform of this signal, and see which one does it better energy compaction. Okay, so this is a little MATLAB script. You can take a look at it later to see how it was generated, but it primarily used just the, for DFT, I actually just used the DFT MTX command of MATLAB. And for DCT, I simply use the DCT MTX command. Okay. So this is what the signal looks like, x of n, for n, capital N equal to 32. Okay. And this is a sinusoid which is decaying with time. And now we can compute its discrete Fourier transform coefficients. And they are listed here. These are the discrete Fourier transform coefficients. And as you can see, even though it's a sinusoid, it's not a pure sinusoid, it's decaying. And because of that, if you look at the 32 DFT coefficients, while there are some large ones and a few small ones, none of them are really close to 0. When you look at the transform of any signal and you see this kind of a property, that is just an immediate way of seeing whether that transform does good job of compressibility or giving you a good k-term approximation or does a good job of energy compaction. And you can see that for the DFT coefficient, they are not very close to 0. Okay, so these are the raw DFT coefficients. They are absolute values. I haven't changed the indices. I can also sort them by descending order of magnitude, and those are the same DFT coefficients. So for energy compaction, that's a really good way of seeing how much energy is concentrated in a few coefficients. So you see that there are two really big energy coefficients in your DFT. Then you have a few, two more, then two more, and then there is a slow decay of the other coefficients. Right? But none of them are getting really close to zero. And this means that if I were to construct a signal by throwing out any of the coefficients, I will lose some information. Okay? And the information won't be that negligible because the height of these coefficients is like 0.1. So these remaining coefficients, if I decided that I'm going to throw all these coefficients out and construct my signal by keeping only the larger ones and using the columns corresponding to these coefficients, my error will not be negligible. And this is indeed what I am plotting here. So I want you to focus on this blue curve, which this is the mean squared error as I had defined earlier, x minus xk star, the 2 norm squared. So this is just measuring if I throw all my coefficients and keep only the k largest ones, and I construct a signal from that, what is the error of that signal to my original signal, which I showed you above, this one. Okay. So on the y-axis you have the error, on the x-axis you have the value of capital K. Okay. So when k equal to 1, I believe I start at 1, this is the amount of error that I get. When k equal to 2, this is the amount of error that I get. Okay. It is, of course, as I use more and more coefficients, as k becomes larger, I'm using more and more coefficients. As I use more and more coefficients, of course, my error is going to go down, but it never hits 0 till I use all of my coefficients. So for k equal to 3, I get here, I keep on going down, but I never hit 0 or even get close to 0 till I really am using almost all my coefficients. And I hit 0, of course, when I use all of my coefficients. Right? So this shows that the discrete Fourier transform is doing a really bad job of capturing energy in your signal in a few coefficients. Now let's take a look at the same signal but using discrete cosine transform. These are the magnitudes not in, I haven't put them in a sorted order. Okay, so the first coefficient is this one. It's a little small. It keeps on going big. But after a while, about 5 or 6 coefficients later, your coefficients are almost hitting 0. Okay? They have become really small. So just a figure like this where you have a few large coefficients and the others are really small tell you that that transform is doing a really good job of expressing most of the energy in your signal. Okay? And now I'm just plotting the sorted ones. If you plot the sorted coefficients, then you can actually do one-to-one comparison with the DFT versus the DCT. So let's look at these two plots on the farther right side of you. So the DCT has a really big coefficient, then two other larger ones, then another large one, a few more, and then after 1, 2, 3, 4, 5, 6, 7, after 7 coefficients, the other coefficients are becoming really small. Compare that to the one above. After 7, they still have a lot of energy left in them. Okay? And what this means is that if I use now DCT to construct approximations of my signal by throwing away most of the DCT coefficients, and I record the error. Of course, if I use k too small, so if I use k equal to 1, my error is nowhere close to 0. It is still very small compared to DFT, but it is nowhere close to 0. But as I increase k, I go to k equal to 2, I go really small. K equal to 3, further small. 4, 5, 6, and up to 7, it seems as if my error has almost become 0. Okay? So this signal, which is a 32 length signal, most of the energy in it can be described using only 7 DCT coefficients. Whereas if you stored the signal in its original form, you would have to store 32 numbers. Or if you used DFT, you would still have to store 32 numbers because the error is very large till you get k almost equal to 31 and 32. So that's a demonstration of the power of discrete cosine transform. And in fact, for a long time, discrete cosine transform was one of the main things that enabled image compression, the 2D discrete cosine transform, of course. But that is what was enabling image compression. Okay? The idea was almost just finer details behind this, that you take the 2D discrete cosine transform of your image, you keep only the coefficients that are large, you store them. And that's how you do compression. I'm of course skipping all the other details related to quantization, but the basic principle was pretty much this. And what would end up happening is that an image, which will probably have, like, let's say 10 million pixels, which is effectively, if you talk about grayscale, 10 million numbers, you can store them by perhaps using only 2 million numbers. That's a compression by a factor of 5. So discrete cosine transform is really good in terms of capturing energy in smooth signals, signals that are slowly varying. Okay, so we have talked about DCT being better than DFT in terms of capturing energy in signals that are smooth, and if they are smooth, then by necessity they have to be pretty stationary. They can't have too high of transients. For signals which have transients, they are non-stationary, you get sort of a blip at some time and then they die down. We looked at another transform, the short-time Fourier transform. And while short-time Fourier transform is really good in terms of capturing transients, it does have one major limitation, which is that you have to fix the time and frequency resolution at all, for all frequencies and all times simultaneously. Okay, so let's see what it means. So let's take the example of a transient, a signal which has transient, say xn consists of 2 transients. So here is your signal. You are interested in looking at it from this starting point to end point, and the signal has sort of a smooth component, okay, and then it has this sort of really transient signal afterward, And you can now compute its short time Fourier transform to figure out that, okay, at this time there was some energy, so this part of the signal, of course, is smooth, which means it consists mostly of low frequencies. So up to this point, you could say that you have certain block of low frequencies, so you will have some information here. Okay. And then in this region, you have this transient, which is really sharp, which means that this part of the signal has mostly high frequencies. Right? So if you were to look at the spectrogram, which is just the magnitude squared of your short time Fourier transform, you'll probably see some energy in this region. Now, the short time Fourier transform that you constructed, it is of course based upon some window. So the short time Fourier transform relies on a window W of n, and based upon the length of the window simultaneously is going to set your time resolution and your frequency resolution. For example, if your length of your window was large, then you will have actually some leakage around the time. Right? You won't have that good of a time resolution. You can't tell when exactly a signal started and when it ended because you're using a large window. Okay. On the other hand, if you used a large window, then you have a really sharp boundary around your frequency edges. Okay. Now let's say that you want to, because you have this transient, you really want to be able to distinguish where this high frequency component ends and where it begins. Because in most cases, high frequency components, if you think about signals, high frequency is where most of the action at some level is taking place. Right? So you really want to pinpoint where this thing appears and finishes, and for that, if you want good time resolution, the natural thing to do will be that you reduce the length of Wn. Now we are only interested in the time resolution in relation to the high frequency. We are fine with the low frequency. But the short time Fourier transform has no distinction between the two. It's going to give you really sharp transition here if you reduce the length of the window. And around these edges, you will have a really sharp transition. But what will be the effect of that on frequency? It's now going to give you really bad resolution in frequency in all this region. Okay. And the reason for that is that short time Fourier transform treats the time and frequency plane in a uniform manner. It doesn't care whether a region is in low frequency or in high frequency. Okay. If you want a better resolution in some plane, in time frequency plane, it doesn't matter where that region is. You do something to one region. For example, if you want to do something in this region, you are going to get its effects in this region. Okay? So the canonical term that is used is that short time Fourier transform divides the time frequency plane. Right? I hope everyone was comfortable with the fact that this is time and this is frequency, as we have done in the earlier classes. So short-time Fourier transform divides your time frequency plane in a uniform manner. So you often come across figures like this, where this is your time and this is your frequency, where the short-time Fourier transform divides the grid of time and frequency into equal-sized cells. As you change your length of the window and the characteristics of the window, all of these cells change in the same manner. If one cell gets larger, the other is going to get larger. If one cell gets smaller, the other is going to get smaller. Wavelets, on the other hand, basically let you get away with this. They are effectively doing a tiling of your time frequency plane in a manner which is analogous to the short time Fourier transform, but the tiling is not uniform. Okay. What it does is it gives you a tiling which has this kind of a nature. At low frequencies, so these are low frequencies, okay, and these are high frequencies. At low frequencies, it gives you low time resolution, but high frequency resolution. And as you go in high frequencies, it gives you better time resolution. So high frequencies, you can really tell apart where a signal started and ended. And of course, the shapes of these things will change based upon, just like there is something called window in short-time Fourier transform, in wavelets there is something called the mother wavelet, which decides the shape of these tiles. But the main idea is that wavelet transform in general does not give you this uniform tiling of the time frequency plane as opposed to the short-time Fourier transform. Now, there are many ways to define wavelet transforms and many ways of interpreting wavelet transforms. We are only going to try and scratch the surface by giving you some broader ideas, so that if you are interested, you can go beyond this class and look up other text or perhaps take other classes. So wavelet transform, just like the Fourier transform world, you have continuous wavelet transform, you have the discrete time wavelet transform, and then for computational purposes, you have the discrete wavelet transform, which is analogous to the discrete Fourier transform. Just like the discrete Fourier transform can be computed in linear computation time. If you have length-hand signal, you don't really have to explicitly compute it. You can use these kinds of algorithms like the fast Fourier transform to compute it in order n log n computation time. Discrete wavelet transform can also be computed in a very fast fashion. Discrete wavelet transforms can be used for spectral analysis if you are interested. They have really good energy compaction properties, especially for signals which have transients or which have discontinuities. So wavelets are now, in the current standard of JPEG compression, for example, wavelets have a central role to play. All the compression is based upon the wavelet transform. We'll only look at few basic ideas behind wavelet transform, and our treatment will be at times rigorous, at other times it will be more intuitive rather than rigorous. So we'll start that discussion formally in the next class.